Today we're going to start working on simplifying non-perfect square roots. So last week we learned what a perfect square is, and we know that a perfect square is a number like 16 because you can take the square root of 16 and get 4 easily because 4 times 4 is 16. We know that 100 is a perfect square because 10 times 10 is 100. We know that 400 is a perfect square because 20 times 20 is 400, and so on. So now you're going to see how that can be used to simplify any non-perfect squares. So our first step when we're doing this is to create a factor tree of the number under the radical. Radical is a fancy term for square root. So that radical symbol is the square root symbol. Express the number as a product of primes under the radical. Product of primes is when you get all the prime numbers that make that number, and we do that by making a factor tree. 3, any prime that occurs an even number of times is a perfect square. Take the square root of the numbers from step 3 and rewrite the square root as the product of the number found in step 4 and the remaining square root. So I know that sounds tricky, but once we start doing it, you will understand. So let's take a look at number 1. What is another way to write square root of 20? So 20, if we make a factor tree, is 2 times 10, which is 2 is prime, so we're going to circle that. And 10 is 2 times 5, both prime, so we circle those. So our new square root, another way to write square root of 20, is 2 times 2 times 5. Now again, any number that shows up an even number of times represents a perfect square. So 2 times 2 is a perfect square. And we know 2 times 2 is 4, which is a perfect square. So now we have 4 times 5. So now we take the square root of the number we can, leave the number we can't. So the square root of 4 is 2. That comes outside of the radical. 5, we can't take its square root, so it stays under the radical. So 2 square root 5 is the same as square root of 20. I can prove it because if I take my calculator and I do the square root of 20, I get 4.47213. And if I do square root 5 times 2, I get the same, 4.47213. Okay, so they are equivalent. It's just a simplified version. All right, so let's take a look at the square root of 28. Similarly, we start by making our factor tree. 28 is 2 times 14. 2 is prime. 14 is 2 times 7, both prime. So the square root of 28 can be expressed as 2 times 2 times 7. Again, any prime number that shows up an even number of times represents a perfect square. So this 2 times 2 is a perfect square, which is 4 times 7. We take the square root of the number we can. Square root of 4 is 2. Leave the number we can't. Square root of 7 stays. So 2 radical 7 or 2 square root 7 is our simplified answer. Okay, so I'm going to go through a bunch of examples with you, and then you're going to try some on your own, and then tomorrow you're going to do some more practice with this, because this is a really important skill, especially for those of you going into algebra next year. All right, so number 3, we have the square root of 50. So again, we start by making our factor tree. 50 is 2 times 25. 2 is prime. 25 is 5 times 5, both prime. So under our radical, we're going to put 2 times 5 times 5. Any number that shows up an even number of times is a perfect square. So 5 times 5 is our perfect square. So we get 25 times 2. Take the square root of what you can, leave what you can't. So the square root of 25 is 5. Square root of 2 stays, making our answer 5 radical 2. On to number 4. Start by making your factor tree. 98 is 2 times 49. 49 is 7 times 7, all of which are prime. So underneath our radical, we have 2 times 7 times 7. 7 shows up an even number of times, so that's our perfect square, which is 49 times 2. Square root of 49 is 7. Can't take the square root of 2, so that stays, leaving our answer as 7 radical 2. All right, let's try the next 2. Square root of 18. We start by making our factor tree. 18 is 3 times 6, and 3 is prime. 6 is 2 times 3, both of which are prime. We list those prime numbers under our square root, and we get 2 times 3 times 3. When you're listing, it's always nice if you just start from least to greatest out of the prime numbers that are there. 3 shows up twice, so 3 times 3 is our perfect square. So we have 9 times 2. We can take the square root of 9. Square root of 9 is 3, and we leave the square root of 2, making square root of 18 equivalent to 3 square root 2. Okay, square root of 44, we do the same thing. We make our factor tree. 44 is 4 times 11. 4 is 2 times 2. So underneath our radical, we have 2 times 2 times 11. 2 times 2 is our perfect square, so it's 4 times 11. And the square root of 4 is 2, but we can't take the square root of 11, so it stays in the radical, making square root of 44 equivalent to 2 square root 11. Okay, number 7. Now we're going to get a little bit bigger because we've got a harder number here, but we start with 243. 243 is not divisible by 2, but it is divisible by 3. And I know that because 3 goes into 24 and 3 goes into 3. So 3 goes into 24 8 times, and 3 goes into 3 once, so it's 81. 81 is 9 times 9. 9 is 3 times 3, and 3 times 3 again. So I have 1, 2, 3, 4, 5 threes. And again, the rule is that any number that shows up an even number of times is a perfect square. So we have 5 threes, but 4 of those threes makes a perfect square. And you might have noticed it in the factor tree that 3 times 3 times 3 times 3 is 9 times 9, which is 81. So it's 81 square root 3. Square root of 81 is 9, but I cannot take the square root of 3, so I leave it. 9 square root 3 is equivalent to the square root of 243. All right, last one I'm going to do with you is square root of 75. 75 is 5 and 15. 5 times 15 is 75. 5 is prime. 15 is 3 times 5, both of which are prime. So under my radical, I have 3 times 3 times 5. 3 times 3 is our perfect square, which is 9. So it's 9 times 5. Square root of 9 is 3. Square root of 5 can't be done. So our final answer is 3 radical 5. Okay, so when you're doing the next couple problems, make sure you're making your factor tree. It might be helpful to refer to the list of perfect squares that is in the notes on the previous page.